Hello everyone, in this video we will continue examining topic 5.4, the magnetic effects of electric currents, and we will unpack the components of a Bainbridge mass spectrometer. So, as discussed before, a Bainbridge mass spec measures the mass of individual nuclides. The first thing you want to do to use it, first thing you need to do is take your sample, the sample which contains the particles whose mass you wish to measure, and you need to vaporize and ionize the sample. So usually this is a small amount of material, and you vaporize it and ionize it. And so you convert your atoms with with proton number Z and mass number A to individual ions. You strip off an electron or two most commonly. Then in step 2, which looks like this, you take those ions, you place them in between two charged plates, and you apply a potential difference to accelerate those ions to different velocities. So those ions are sort of injected in this region, and the potential difference held across these two charged plates accelerates those ions towards a small opening over here, where some of the ions pass through. Notice that if you're applying a delta V, then you can calculate the change in the kinetic energy by using the definition of potential difference. The definition of potential difference is the work per unit charge, and therefore the charge times the potential difference is the change in the kinetic energy gained by the ions here. And because they start out not moving at a particular velocity, their change in the kinetic energy is just equal to 1/2 mv squared. And you set that equal to q times delta v and solve for the velocity of those particles. And that gives you v equals the square root of 2q times delta v divided by m, which means you can calculate the velocity of the particles if you know the potential difference they have been accelerated through. Now in practice, the problem is that some of the particles start out here, and some of the particles start out here. Or here, for that matter. And so they accelerate by different amounts. So what this value is then is a maximum velocity given the potential difference here. This is the velocity of the particles that start out furthest away from the opening. So this places sort of an upper bound on that velocity. Okay? Then in step 3, you send these particles through that opening through this region here. And in this region, two things are going on. One is you have a magnetic field going into the page, or out of it for that matter, but it's sort of into or out of the page here. And you have an electric field at right angles to that magnetic field. And the electric field and the magnetic field you have are chosen so that the magnetic force and the electric force that those fields apply to the particle are in opposite directions. This particular component is called a velocity selector because of the following effect. Consider what happens when you have your charged positive ion moving to the right in this region. It feels a magnetic force upwards and an electric force downwards. Consider what happens if it makes it through all the way to the end through this opening. Well, if it made it through all the way to the end, that means that the force, the net force on that charged particle as it moved through this region was 0, which means the magnetic force was equal to the electric force. So if, for a charged particle, if it makes it all the way through, and the magnetic force is therefore equal to the electric force, then we can say that QVB is equal to Q times E. The Q's cancel, and what that means is, for any particle that makes it all the way through the velocity selector, we know the velocity. Why? Because we control the electric field and we control the magnetic field. We know what those values are. That gives us the value for the velocity of the particles that come through the velocity selector. So big picture, right? We cross our electric fields and our magnetic fields at right angles so that the forces induced by those fields cancel out. And when they exactly cancel out, then we can determine the velocity. And notice we can change, right? So let's say it's not perfect, it's not exactly the velocity we want. We can adjust the electric field and the magnetic field until these particles make it all the way through. So let's say we're miscalibrated at the beginning, then what we can do is simply adjust the electric field strength until the particles are making it through, at which point we know what their velocity is. Notice what happens if a particle comes in that is faster than that. Well, if it's faster than that, it will feel a magnetic force that's stronger, but it will feel the same electric force. And so if it's moving too fast, it will end up pulled in this direction and will run into the wall over here. If it's moving too slowly, then the magnetic force is weaker than the electric force. Notice the electric force stays the same strength the whole time, at which point it will run into this side. So when particles make it all the way through that opening, we know they have exactly this velocity. And that's really the most important part of this step. Then, finally, we send it into a region with a uniform magnetic field. Could be the same magnetic field as here, but does not have to be. Because this is a charged particle moving at a known velocity in a uniform magnetic field, it will travel according to uniform circular motion, and we will detect it with a detector placed right here. It travels in uniform circular motion with radius equal to m over q times v over b, which means that if you solve for m, you can get an expression for the mass of that particle in terms of the radius, which you measure, the charge, which you know, the magnetic field, which you control, and the velocity, which you just selected with step 3. And if you know all these things, you can measure the mass of that individual particle with this particular setup. So that is the power of the Bainbridge mass spectrometer, that you can measure the mass of the charged particle moving in this uniform magnetic field by measuring the radius of circular motion and knowing the other variables. Notice what happens if you get an ion that has the wrong charge. Okay, it has the wrong charge, +2, +3. Well, notice it's actually going to make it through step 3 because the charge cancels out. But in step 4, that charged particle, if it has a +2 charge rather than a +1 charge, for example, will have a simply much higher radius. And so you won't detect them anywhere near where your detector actually is. Notice that this means that small differences in mass will create noticeable differences in radius for high enough speeds. So you can detect the difference between, for example, uranium-235 and uranium-238 using this method. The radii will not be tremendously different, but as long as this circle is wide enough and your detector is sensitive enough, you can tell the difference. And so that's how a Bainbridge mass spectrometer works.